Have you ever looked at something and just wondered how it works? From a simple desk lamp to some complex machine? Well, a lot of the time, the secret is hiding in a surprisingly simple shape, the parallelogram. Today, we're going to build a full geometry toolkit to understand exactly what makes this shape so special.
Okay, check out this classic desk lamp. How does it move up and down so smoothly but always stay perfectly balanced? It's not magic, it's geometry. And it all comes down to the simple, powerful properties of the parallelogram, which are the key to its stability. Let's dive in and see how.
So, what's the official definition? A parallelogram is a quadrilateral, which is just a fancy word for any four-sided shape, where both pairs of opposite sides are parallel. That's it. That's the one core rule, and every other amazing property we're about to uncover stems directly from this one simple idea.
So let's make sure we have that basic blueprint down cold. What does parallel really mean here?
You see those little arrows on the sides? In geometry, that's the universal sign for parallel. It means the top and bottom sides are like two train tracks that run alongside each other forever and will never, ever cross. And it's the same deal for the left and right sides. That's the entire blueprint right there.
Okay, so we've got the blueprint. Now let's start adding some tools to our toolkit. We'll start with 3 foundational tools that cover the sides and angles. Honestly, these are the ones you're going to use all the time.
Tool number 1 is simple, but it is so powerful. Opposite sides aren't just parallel, they're also congruent. And congruent is just the geometry way of saying they're the exact same length. So the top side is always the same length as the bottom, and the left is the same as the right. Always.
All right, let's put that first tool to the test. In this parallelogram, we can see that the bottom side has a length of 12 units. So what does that tell us about the top side, which is labeled x plus 4?
Well, since we know those opposite sides have to be equal, we can set up a really simple equation. The top side, x plus 4, has to equal the bottom side, 12.
Just a little bit of quick algebra, subtract 4 from both sides, and boom, x has to be 8. And that's the whole point. If x was anything else, this shape just wouldn't be a parallelogram anymore. The properties tell us what the numbers have to be. Okay, time for the next tool in our kit. This one's about the angles. And the rule is just as simple. Just like the sides, the angles directly across from each other are also congruent. They're a perfect copy.
So let's go back to our example. We're told that the angle down in the bottom right corner is 65 degrees. So, using our new opposite angles tool, what does that angle in the top left, the one labeled y, have to be?
You got it. It has to be 65 degrees. If the angle at C is 65, then the angle at A must also be 65. They're a perfect match. You don't need a calculator or anything, you just need to know the rule.
And here's our third key tool. This one deals with consecutive angles, which just means any two angles that are right next to each other. The rule says they are supplementary, which is just a fancy way of saying they will always add up to a perfect 180 degrees. And that brings us right back to our lamp. This property is the real secret to its stability. So if we know that wider angle is 110 degrees, our new rule lets us find the sharper angle right next to it in a snap. We know they have to add up to 180.
So 180 minus 110? That leaves us with 70 degrees. It's this perfect mathematical relationship that keeps the lamp balanced. As one angle gets wider, the one next to it has to get smaller by the exact same amount. That's what allows the whole thing to move so smoothly without just falling apart.
Okay, so we've covered the sides and the angles. Now it's time to add a more specialized tool to our kit. This one isn't about the edges of the shape, it's about the lines that cross right through the middle. These lines are called the diagonals. They connect the opposite corners. And the rule for them is simple. They always bisect each other. Bisect is just a great geometry word that means to cut into two perfectly equal halves. So that point where they cross is the exact middle of both of those lines. And this property gives us a really cool shortcut. If you have a parallelogram on a coordinate grid, that intersection point is the exact midpoint of both diagonals. That means you can find the dead center of the entire shape just by finding the midpoint of one of those diagonal lines. Pretty neat, huh? So now it's time for the ultimate test. Let's take our new toolkit and put it to work on a coordinate grid. This is where all these abstract rules become really powerful problem-solving tools. So imagine this. You're given 3 corners of a parallelogram on a graph. How in the world do you find the exact location of that 4th missing corner? Well, the answer is in the very first rule we learned. Opposite sides have to be parallel. And on a grid,
Parallel simply means they have the exact same slope.
And here's exactly how that works. First, we find the slope of one of the sides. So to get from W to X, we go up 5 units and to the right 2. Now, because we know opposite sides have to be parallel, the side across from it must have the exact same slope. So we just go to the opposite corner, Z, and we apply that same movement, up 5 and right 2, and that lands us perfectly on our missing point Y. It's like a little treasure map.
Okay, let's do a quick inventory of our brand new geometry toolkit. With just these few key facts, you are totally equipped to handle pretty much any parallelogram problem that's thrown your way.
And here it is, your complete toolkit. Just remember, opposite sides are parallel and they're the same length. Opposite angles are a perfect match. Any two angles next to each other add up to 180. And those diagonals, they slice each other exactly in half. If you master these 5 rules, you've mastered the parallelogram.
And this is really why it all matters. The parallelogram isn't just some random shape in a math book. It's a fundamental piece of engineering. You see it in folding chairs and car jacks and those expandable security gates at the mall. Its simple, reliable properties are what make things in our world move and balance and just plain work. So now that you know the secrets, what are you going to spot next?